Hello everyone, thanks for taking your time to attend my talk. I am Johan and my presentation today will be on the topic of how we can design efficient deep learning pipelines to address the problem of query resource forecast. This research is supported under the GRAB NUS AI Lab, which is a collaboration between National University of Singapore and GRAB. As for me, I myself am a PhD candidate under NUS. Now, Grab is Southeast Asia's super app. Since years ago, the company has expanded its business to cover aspects of transport, food delivery, and digital payments. At its scale, many business decisions must be data-driven. We observe hundreds of thousands of analytic queries issued to our data lake, which is mostly powered by Presto and supporting cloud infrastructure running on AWS or Azure. In this scenario, having a system that accurately forecasts how much resource a query demands would be very beneficial for cost savings. With modern resource orchestration tools such as Kubernetes, Yarn, or Docker, understanding just how much CPU or memory a query needs would enable the developer to request just the right amount of resources that satisfies the query's needs. In doing so, we do not over-provision resources, which leads to costlier query execution, nor do we under-provision resources, which leads to query failure. Our research targets the design of deep learning models to address this problem. As most of the deep learning models at Grab are trained and deployed over cloud resources, having a model that takes a long time to train will amount to large expenses. We want to avoid this. And yet, unfortunately, we argue that present deep learning models are cost inefficient when we apply them over the query patterns at Grab. So at Grab scale, the three V's that are very related to big data, namely velocity, volume, and variety, are taken up quite a few notches. Let's discuss about the first V, which is volume. We noticed the problem of a large number of predicate counts in Grab's query patterns. A sample of 19,000 queries on Grab showed the presence of 30,000 unique predicates. Just for some context here, a common practice for encoding query plans is to take a raw query and translate it into its logical plan. In our case, each node in the plan is either an operator, a table, or a predicate node. A table node denotes the underlying table that is being scanned. The operator denotes the actions taken on the data, such as filter, joins, or projections, and the predicate represents the clauses that the actions are performed over. While it is simple to encode operator and table nodes due to their finite counts, encoding predicates would be a little challenging using state-of-the-art techniques. If we use the one-hot encoding technique over 30,000 predicates, we will end up creating very large and sparse vectors. Using the R vector encoding does help in controlling predicate encoding size, but requires the execution of each query before building the word-to-vec model over the data rows. So imagine if every query takes at least 1 minute to execute. How much time you will have to wait to complete all 19,000 queries? In turn, we propose a way to efficiently encode predicates within a reasonable amount of time. More details will be shared in the subsequent slides. The second V is variety. We hypothesize that the query plans at Grab follow a wider distribution in plan size and depth. To prove this, we surveyed 200,000 query plans and contrasted them with publicly available TBC-DS and TBC-H plans. We observed that the query patterns at Grab cover an even wider distribution of plan sizes and depth. For example, we can have most of the plans having a size less than 1,000 nodes, and then there are a few stragglers having a size over 7,000. Now, the problem here comes with the need for tensor shape consistency when we perform a model training. When we train models over all query plans at Grab, we have to pad the smallest plans to the shape of the largest. And this process introduces unnecessary information that makes the overall input size larger. Consequently, computational requirements and data transfer overhead are larger. Now, the final V is velocity. Grab's query patterns are evolving at a very fast rate. we conducted a simple study where we analyzed all tables scanned from 373,000 queries over a span of 1 month. Thereafter, we looked at the adjacent window of 1 to 9 days and quantified the number of tables not present in the original set over that month. The reason for doing so is to evaluate how fast we need to retrain our deep learning models in light of new tables being introduced. We observed that when W equals to 9, almost 12% of the tables out of the original set are new. And if we train our model using 1 month's data and deploy it to predict queries 9 days later, we can expect a large deterioration in model performance. So in practice, we would recommend daily retraining of our models. We summarize the challenges and research opportunities in training models over query patterns at the scale of grep. Because we need to retrain our model frequently, it's important to bring down model training costs. We showed this in our work by proposing 2 techniques in the deep learning pipeline. We are able to reduce model training costs by up to a factor of 13x and also achieve better resource forecast accuracies than our selected comparisons. Our first innovation ensures that all query predicates can be efficiently encoded. We do this by training a word-to-vec model directly on the predicates themselves. Here's a toy example to illustrate the point. We first strip the predicates of all values and the remaining tokens are grouped under a fixed window size. These groups will then be used to train a word-to-vec model to derive token embeddings. In this case, if orders and ID occur frequently within all query plans, then we will expect that their embeddings must be very similar to each other. After training the model, we cast the predicate as a syntax tree. The leaves of that tree contain the individual clauses, and the nodes contain the conjunctions. We use our model to encode all leaf nodes by taking the mean of all tokens in the leaf. We resolve conjunctions by using the min mx pooling for the n and all nodes respectively. By using this approach, we are able to define a fixed token embedding length and learn predicate representations within a reasonable span of time. Thereafter, we propose our pipeline that is based on tree convolution. One of the early works for tree convolution comes from the research done by Marcus et al. The authors propose a model that uses triangular kernels to perform convolution over query trees. Each layer of the convolution preserves the original shape of the tree and attempts to extract meta features from the spatial arrangement of all nodes within the tree. Here we adopt a similar practice but introduce the notion of subtree convolution. This process minimizes the input size to the model. So instead of working with the full query plan, our model will work with the top n selected subtrees. We call our model pipeline Prestroid. Now, the crux of a subtree decomposition algorithm lies in the observation that for a single kernel and 1 layer of convolution, each node only requires information from its first layer of children. Hence, if we say that we want to decompose the tree such that each subtree has a capacity of n nodes and L layers of convolution, then starting from the root node, we recurse down the tree breadth first until we exceed the quota of n. Note that each time we traverse down the depth of the tree, we must always materialize all children at that depth. This is to ensure that the parent nodes have complete information present from the child nodes during our convolution. In this example, we see that if we cut the tree at depth 4, the resultant subtree will have a size of 9, which is beyond 8. Hence, we must cut the tree at depth 3. In doing so, only the nodes of S1 in green have complete information. The nodes in red have their children removed and do not have complete information. We apply bit masking on these nodes to negate their information. Thereafter, we cut the tree at depth 2 and repeat the algorithm, assuming that the roots are now D, E, F, and G. The resultant subtrees are denoted on the right. With this, we can envision a system which uses Prestroid to guide resource provisioning for ad hoc queries. When an analyst submits his query, we would first pass it into a syntax tree and apply our encoding and subsampling techniques. Our trained Prestroid model will then predict the needed amount of resources for the query and request the resource controller to create VMs on the fly for the right specification to execute the query. We test pressurized and selected models under 3 different experiments. The first is an MSE scoring experiment to evaluate query resource forecasts. The second is a resource allocation experiment to quantify resource savings when we deploy pressurized. And the last is an experiment where we evaluate the cost savings of pressurized under cloud environments. We use our in-house grep tracers and publicly available TBCDS dataset for our experiments. For grep tracers, we have a total of 200,000 query plans, and we adopt a split of 8-1-1 for training, testing, and validation dataset, respectively. For TBCDS, we have a total of 5,000 query plans generated from 83 publicly available templates. Again, we adopt a split of 8-1-1. Also, we selected 4 models for comparison. They are a support vector regression model, a word convolution model, MSCN, and full tree convolution. In the interest of time, please refer to their references to understand more details of their implementation. Now, for our first experiment, we see that certain configurations of pressurized enable the model to achieve the highest degree of accuracy for grep tracers and TBCDS dataset. For grep tracers, we also achieve the lowest number of approaches to convergence. Now, this experiment highlights 2 important details. The first is that tree convolution-based models are generally more performant relative to the non-tree convolution-based counterparts. This is because query performance is very sensitive to the order of execution within a query plan. A simple swap of 2 nodes within the plan can result in a great difference in the time needed to execute the query. Hence, when inferring features from a query, it is imperative that we account for the spatial arrangement of nodes within the plan. In addition, the use of subtrees in pressurized enable queries to be represented with n times more features relative to full tree convolution. This helps the model learn the finer details for more accurate resource mappings. In our second experiment, we showed that pressurized fared better at resource provisioning relative to full tree convolution models. While in general, all models tend to under-provision resources, pressurized provision resources closer to what was desired. This is important for grep, as what good is it to build a model that is fast and cheap, yet compromising on the resource forecast accuracy during deployment. Finally, in our last experiment, we compared the average per epoch runtime and batch size of pressurized relative to other models. Now, with exception to WCNN, pressurized models are faster to train and have lower memory footprint. These efficiencies pay off during model training over large batch sizes. For example, with a batch size of 256, we are able to train pressurized models over single GPU instances. Whereas for full tree models, we have to train them over multiple GPUs under data parallelism. In doing so, we incur significant communication overhead that makes the multi-GPU cluster costlier to use. We showed that with pressurized, we are able to achieve a 13-fold reduction in model training as compared to full tree models. Now, do note that despite WCNN's showing of low memory footprint and very fast epoch timings, we have showed in our prior slides that pressurized models have far better resource forecasting accuracies. We argue that having good resource forecasting accuracies should be our first priority when we choose our model. In summary, what we have done for our research is to investigate the design of deep learning models that can be practically deployed over industry-realistic query benchmarks, yet achieving high accuracies in query resource forecasts and are also cost efficient in training over cloud resources. Before we end, we would like to mention that we are open sourcing our grep tracers and TBCDS dataset. The link is found in this slide. In addition, we are also releasing our technical report that can be found on the archive, and the link is found in this slide as well. Thank you for taking your time to listen to my talk, and I'd like to take any further questions.